So let us now consider what these basic facts that we've proved regarding purity, how they then lead us to the conclusion that bound states must either be always even or odd. So to do that, let's first consider the relationships that we can expect between parity and the Hamiltonian. So this first set of considerations that we will be looking at really just allow us to consider what happens when we change our coordinate system. So we'll begin by considering a change in our coordinate system. After all, that is what parity actually accomplishes for us, as we had mentioned up here. So we could, for example, imagine having some function f of x, here he is like so, and I'll give you a sketch for him, so he'll look maybe something like so. And then if I imagine just again changing the direction of my x-axis to be pointing in the other direction, and then consider what my function must look like, it will then have this appearance where, notice I drew my first function a little bit asymmetric, so it will have less of a tail on this side and it will have its hump here on the other side of the axis. This is then a picture of what the parity operator would look like when applied to my function f of x. Right, so it's just really a change in coordinate system. Now, to relate this to the Hamiltonian, let's imagine that I apply my Hamiltonian to my function f of x. So here again is x. I'm back in my normal coordinate system. And I'm going to imagine that my Hamiltonian, it's just, this is just for an arbitrary sketch to just kind of think about things conceptually, just so that I can draw a sketch. Let's imagine the Hamiltonian something pretty simple. It's an operator, so I'll have this Hamiltonian operator applied to f of x. And maybe what this Hamiltonian does to this f of x is it just puts a little dent in the function at some value here. I'll call it x equals d, say, right, where the dent is going to happen. And then, I would have, again, I'd have my tail here, but most of the effect happens near D, where there's going to be a little dent in my function. Maybe it will look something like this. That's the Hamiltonian acting on my function f of x. Now, I can also consider then what things would look like in my flipped coordinate system. Right? So in my flipped coordinate system, there's going to be some corresponding Hamiltonian operator, which is what the Hamiltonian operator looks like under this change in coordinates, where x has gone to minus x. So again, this first line of pictures is really my standard coordinates. And this line here are going to be my flipped coordinates. And if I apply my Hamiltonian, my appropriate flipped Hamiltonian that applies to these flipped coordinates, I know what it is that I should get, right? I'm going to start off with my regular function, but it's going to develop a dent. But because things have been flipped around on me, the dent will develop at location minus d, and it will look maybe something like so. So this picture is a result of applying the Hamiltonian in the flipped coordinate system, which I'll call h sub fl for flipped, and I've applied that to the flipped version of my function. Now, what I hope you can see is that, well, this function here, although my diagram didn't come out so well, really should be a perfect match for my function up here. So I'm going to redraw it a little bit so it looks a little bit more like it had, right? This is really just the flipped version of the Hamiltonian applied to my function in the normal coordinate system. So I should be able to conclude then for any function f of x, I expect to find then that the flipped Hamiltonian applied to the flipped version of my function, which is what I've sketched for you here, really should be the same thing that I would have gotten if I had applied the Hamiltonian in the original coordinate system and then flipped the result. Because after all, right, I'm not making right now any claims about the form of my Hamiltonian. I'm just writing down the same physical sequence of events, taking my function and applying the Hamiltonian, and I'm just writing down what they look like in two different coordinate systems. So this is really just looking at how things look in different coordinates. Now, because this relationship, notice, should hold for any function f of x regardless of the function, that then tells us, because this is for any f of x, that means therefore that so we can conclude then that the flipped Hamiltonian acting on the parity operator as an operator, right? This operator is the same as this operator, is the same as doing the operation in the opposite sequence, but with the actual Hamiltonian. And if we want to go really crazy with this, we could take the relationship that we have here. We can multiply by the inverse of P on the right side of both of these, and then I would find something like the flipped Hamiltonian times the parity operator times its own inverse, right? I'm multiplying both sides by the inverse. Would be parity acting on H times the inverse of the parity operator. This product, of course, is just 1. And so what I have here really is just a nice equation that tells me what the form of my operator would be in the flipped coordinate system. So this is just, again, a formula for determining the form that I expect for my Hamiltonian in this new coordinate system. So at this point, I've made no real claims regarding symmetry. Let's now think about what symmetry should teach us. So for symmetry, let's think about how we get a physical statement about the form of functions. Well, if we think just in general, if I have my f of x, as we were discussing before, and I apply the parity operator to it, which means I've just gone in there and I flipped the sign on every x that I see, that just gives me f of minus x. At this point, I've made no statement about symmetry. I've just looked at my function in two different coordinate systems. The statement about symmetry comes when I make a claim where I say that my function, viewed in either of these coordinate systems, actually must be equal to itself. When I say that, now I'm making a statement about symmetry, right? Previously, I was just talking about two different ways of looking at my function, but by equating them, that's the moment where I've made a claim then about the symmetry of my function. Likewise, if my Hamiltonian has what is called the parity symmetry, meaning that its form does not change when I switch around my x-axis, that would imply that the flipped version of the Hamiltonian must equal the original version of my Hamiltonian if H has this particular parity symmetry. And I'd like you to notice that what I'm saying here is now a completely general statement that would work for any type of symmetry. For example, if I were thinking about rotations. This formula here, which notice the argument was completely general, I would just put in some kind of rotation operator here. This just tells me what my Hamiltonian would look like in some new rotated coordinate system. Where symmetry comes in is where I say that, well, the Hamiltonian, even when I look at it in a rotated coordinate system, is always exactly the same. That would only happen if the Hamiltonian was, for example, spherically symmetric. Because if it weren't symmetric, rotating the coordinates would then, if it had like a lump in it somewhere, this Hamiltonian, right, rotating the coordinates would then move that lump around and I would see changes in H. But if it obeys the symmetry, I'm saying that the flipped Hamiltonian must match the actual Hamiltonian. And then I could look at this relationship and conclude that if H has this particular symmetry, then, so in general, if H has the symmetry, if H has the symmetry of the operator corresponding to the operator, then because I'm saying the flipped H is the same as the H, I can rewrite this equation, and I find this interesting statement, that the Hamiltonian then, substituting H for H flipped, gives me the same result whether I apply it before or after the parity operator. Or another very quick way to say this is that the parity operator must therefore commute with the Hamiltonian operator. And this, again, is a general conclusion that would work for any symmetry. The way we know that something, that a Hamiltonian has a given symmetry, is we test it by commuting it with the corresponding operator, and if we get 0, we know that it has that symmetry. Now, the fact that any symmetry operator like this commutes with a Hamiltonian immediately has some interesting conclusions. I just want to go over two quick conclusions first. Then we will prove and just verify for ourselves, because the discussion so far has been pretty abstract. Then we will just prove that for the parity operator this actually works. And then we will then get to the real heart of the issue, which is to figure out what this tells us about the bound state functions themselves. But first, just some general quick facts. One of the things we've done with commutators in the past was there's Ehrenfest's theorem, right? So Ehrenfest's theorem will tell us something very interesting here, which tells us that if I look at the time derivative of the average value of the parity of a system, that of course must be 1 over I h bar times the expectation of the commutator of the whatever operator it is with the Hamiltonian, but we just showed this commutator was 0. That tells me then that the average parity of a system never changes. That is the same thing as saying that parity is a conserved quantity. And that general feature actually applies then for any type of symmetry. So for example, there are operators that do rotations on our coordinate system, and those rotation operators will actually be conserved. So there's a lot we can get out of this, but I just wanted to make some quick observations. The other place that we've seen commutators is in the Heisenberg uncertainty principle, which tells me that if I do a series of measurements of the energy on the state of a system, and I look at the spread in those values, and I multiply it by the spread in the values that I can expect from the parity in that system, that must be at least as much as, right? It's the Heisenberg uncertainty principle. It involves this commutator, but the commutator is 0. So this thing has no fundamental limit on it. It is possible. It's possible. So therefore, we see it's possible. It's possible to have, it doesn't prove that it ever happens, but at least now we know it's possible. It's possible to have delta H equals 0 and delta P equals 0 simultaneously in the same state, but delta H equals 0 means I could have a pure state of energy and at the same time a pure state of parity. And it's very gratifying to see that this is possible, because actually, if you think about it, this is actually what we're trying to prove has to happen, right? We're trying to prove that the pure states of energy are pure states of parity, namely even or odd. So at least we know it's possible. Now, so much then for our general considerations that would work for any type of symmetry. Let's go back and just verify that the commutation relation works for parity. So let's check explicitly for the parity case. All right, so we are going to then apply the Hamiltonian to the result of the parity operator acting on an arbitrary function. And what we hope we are going to get, and this is a question mark, we don't know yet, we're trying to prove this, that it will be the parity back again acting on the Hamiltonian acting on my function. Now, we're not going to use this fact, that's just sort of our motivation. I don't want to do a circular argument. What we do know about this is, well, I know how to apply the Hamiltonian. That's minus h bar squared on 2m times 2 spatial derivatives plus multiplication by the potential. And that then is applied to the parity operator acting on f of x, which of course is just then f of minus x. Now I can continue. I know how to take derivatives. So this would be minus h bar squared on 2m times the first derivative of the first derivative of f of minus x, plus then, of course, v of x times f of minus x. Now, this first derivative we know how to take. We have the chain rule. We get the derivative of the function, which I will denote as f prime, evaluated at its argument at minus x. But then we also have the derivative of the insides, which pulls out a minus sign. And so I have this result. So I'm almost there. I just need to take one more derivative. This would be minus h bar squared on twice the mass. When I take the first derivative of minus f prime, the minus sign can factor out. The first derivative of f prime, by the chain rule again, gives me f double prime evaluated at its argument. And once again, I have to take the derivative of the insides, which pulls out another minus sign, so this becomes plus. And then this second term now starts to look interesting, right? Notice what I'm writing down here has a whole lot of minus x's in it, which is very gratifying because, after all, I'm trying to prove that this side of my equation, notice, is the parity operator applied to something. So I would love to get something over here that has minus x's everywhere. And the only thing that's stopping me from that is this annoying, pesky little v of x. But notice, if, I have to assume this, but if v of x is symmetric, right? If it's an even function, then actually v of x will equal v of minus x. So I'm going to underline this. This is my key assumption, right? Apparently, I need this if I want this commutation relation to hold. But if that's true, then I can replace my v of x with v of minus x, which is multiplying, again, of course, f of minus x. And when I look at my result, indeed, this just looks like the parity operator applied to something. And that something is, when I put all the x's back to plus x's, looks exactly like the Hamiltonian applied to my function f of x. And so we've actually explicitly validated for the parity case that indeed we do get the right-hand side. So this deserves a happy professor, I think, particularly because we had known this should happen just based on generic symmetry reasoning, but now we see it happening explicitly. The one condition we need, of course, is that for the Hamiltonian to look the same forwards and backwards in the flipped case and the unflipped case, of course, the potential can't break the symmetry. It itself has to be a symmetric function.